Hello everyone, my name is Longxiang Li. It's a great honor for me to introduce some latest achievement of our Inspur AI&HPC department. Today, the topic of my keynote is building a data-driven scientific workflows with machine learning and HPC applications. HPC is typically used for solving advanced problems and performing research activities through computer simulation and analysis. HPC brings together several technologies such as computer architecture, algorithm, program, and electronics, and require a full system software stack to solve advanced problems efficiently and quickly. HPC systems have the ability to deliver sustained performance through the computing resources. Scientists, engineers, and researchers use HPC for computationally intensive tasks like those used in material science, weather forecasting, and manufacturing. Supercomputer is one of the best-known types of HPC solutions. A supercomputer contains thousands of computer nodes and many software stacks that work together to complete one or more tasks. In history, the scientific research can be summarized into four periods. In the first period was empirical science, where experiments and observations are the main methods of scientific research. Then came the paradigm of theoretical models, characteristic by formulation of various laws in the form of mathematical equations. With the appearance of computers a few decades ago, the third paradigm of computational science became very popular. This has allowed the simulations of complex real-world phenomena based on the theoretical model of the second paradigm. In many scientific research facilities, massive amounts of observational and computational data are being generated every day. For example, China Vast Telescope can generate 3.6 terabytes per hour. The Large Hadron Collider of a European Organization for Nuclear Research can generate 1 petabyte per second. With the increasing amount of data generated by experiments and simulations, the fourth paradigm of big data-driven science appeared over the last few years. It unified the first three paradigms of theory, experiment, and computational simulation. Coupling the scientific model with artificial intelligence methods, especially the machine learning methods, have caused the explosion of interest over the past few years. All of these data can be used to create data-driven scientific workflow with the unlimited goal of creating more accurate, more efficient scientific models. Every one of us may have heard of the top 500 list. It ranks the world's 500 most powerful supercomputers based on their performance as measured by the Impact benchmark. It is published twice per year since 1993 and has evolved to a major source of information about the trends in HPC. Modern HPC clusters are heading towards E-scale supercomputing. The top system, Fugaku, provides about 442 petaflops, which exceeds the performance of Summit at number 2 by 3 times. In single or further reduced precision, Fugaku has a peak performance about 1,000 petaflops. As a result, Fugaku is often introduced as the first E-scale supercomputer. In 2023, it is believed that more E-scale systems will be built one after another, such as the Auro and the Frontier supercomputers. Well, Moore's law has held up remarkably well, delivering a million-fold increase in computational power during the last 20 years. There are also some technology trends appear in the hardware development of the top 500 supercomputers. One of the most notable trends is that the CPU and GPU heterogeneous architecture is widely used for getting high performance. In 2020, there are 146 systems using the GPU accelerator class, including 6 systems of the most top 10 systems. As GPU widely used for AI applications, it also creates a possibility for integration of HPC and machine learning. In terms of a software stack, many compilers and math libraries began to provide support of the heterogeneous platform, enabling the user to better utilize the computational performance, such as Intel's One API toolkit, AMD's ROCm software, and NVIDIA's HPC SDK. All of this software package provides a full capability for developing HPC application on heterogeneous platform, including compiling, performance analyzing, and debugging. In the past, scientific computation and machine learning have often been treated as two different fields with very different scientific paradigms, as the previous one utilizes a theory model and the latter one is data-driven. However, many researchers show that though these approaches are complementary, the physical approaches could directly interpretable and offering the potential of exploration beyond the observation. And the data-driven approaches are highly flexible in adapting to data and finding unexpected patterns. In our practice, to couple the scientific computational workflow with machine learning, the most promising area is improving the prioritization process. Lots of physical models require parameters, but many formulations of a submodel are of semi-empirical nature and cannot be easily derived from the first principle. These parameters are often obtained by some empirical equations or impairment measurement. Machine learning can learn those parameters to optimally describe the ground truths that can observed or generated from the detailed and high-resolution model through the first principle. Furthermore, the machine learning model could replacing this empirical submodel and lead to a hybrid model which combines the strengths of physical modeling and machine learning. Driven by big data science, material informatics has attracted enormous research interest recently, along with many recognized achievements. With the help of machine learning models, a data-driven model runs in a very small fraction of time for doing the simulation, or even bypass the simulation process. However, there is frequently not sufficient database to build a data-driven scientific model. All the available databases do not contain the suitable descriptor of the materials. In the material informatics approach, the electronic charge density determines the property of a material at their ground state in principle. So it is appropriate to be used as a descriptors in material database. However, these databases are difficult to be collected with experimental approaches, especially in the material of high symmetry dense solids with extended structures. On the contrary, the electronic charge density can be accurately simulated by using the first principle computation, such as the dense function theory method. Furthermore, the computational demand of the density function theory is appropriate for realistic materials. So our first work for building the data-driven scientific workflow is building a material informatics database by using the state-of-art first principle calculation. This figure shows the overview of a workflow to build a material informatics database. The database, we mainly focus on the material in qubit symmetry, which require less computational amount and are more efficient to be calculated. The framework contains 4 parts. The first step is the pre-processing. In the pre-processing, we use a query method from the Python material genomatic package and the actual structures and pseudo potential K-match fields from the material project. To improve the computational efficiency, we use MPI package to rebuild a paravision of the material genomatics. In the second step, we apply the density function theory to compute the electronic charge density of all the candidates. We prepare all the parameters in the in-car fields, which contains a lot of control parameters for running the vast jobs. During the optimization, two converge steps are required. This calculation are performed until the maximum force and the engineering components are small enough. After fully converged, the electronic charge density of all the materials are calculated separately in the self-consistent process. The electronic charge density was first stored in the CAG format, but the JSON format is more famous in the machine learning researches and can be integrated in other databases. So in the third step, we converted the result from the CAG to JSON format. In the last step, we have made some data analysis with the results, such as the distribution of the space group, volume, and the number of atoms in the unit cell and elements. Finally, we obtain a real space of electronic charge density database, which contains 17,480 qubits in organic materials. To the best of our knowledge, there is no similar database today. The database is obtained by performing expensive density function theory calculation, which is supported by China's Central South University. The computation used 14,400 CPU cores running for 2 months. The result database volume is larger than most of the databases available today. We believe that it will be available for a wide diversity of electronic structure analysis and related machine learning studies. Here we show several patterns of the calculated electronic charge density and compare them with those reported in previous studies. This could verify the correctness of our simulation and database. The research paper about our material database have been accepted by Scientific Date this year. The material database is also available online. This is the first step of our work to couple the machine learning with the material science researches. Based on the large electronic charge density database, we will try more possibilities to develop a data-driven material science and technology. The second area for covering the machine learning is the CFD modeling. In CFD models, calculation of toppling flow is one of the most challenging problems in all of the science and mathematics. Toppling flows are characterized by a large range of versional structure at different scales, which interact with each other and exchange energy. So correctly modeling the toppling flow is a key part in CFD modeling. There are mainly three approaches. Those are the RANS, the LES, and the DNS approaches. The main difference among these three approaches are the resolution of scales. From the right figure, we can see the velocity fluctuations of different models changes with time. So LES and DNS provide more accurate results. They are also very computationally expensive and is more suitable to perform fundamental studies. As shown in above figure, in order to simulate the error fault modeling with the LES models, we need a supercomputer with its computational ability to achieve T-scale or P-scale flows. This is almost impossible for most of CFD engineers or researchers. Therefore, the RANS modeling is the most common and widespread approaches in engineer practice during the foresee future. In the toppling model, computation over the Reynolds stress term is the main part. In traditional toppling models, such as standard K-Easton model, the Reynolds stress can be obtained by solving the partial differential equations. However, the universality of this model is limited, as some prescribed parameters should be determined beforehand, which are derived from some experiments. The machine learning approaches have shown their potential to solve the shortcoming. Our approach directly reconstructs a mapping function between the renal stress terms and the mean flow variables. With a natural network, we completely avoided solving the original partial differential equations. The results calculated by the DNS model are taken as the training date to construct a high-dimensional data-driven network model with machine learning methods. This figure demonstrates the results of the carbon model in the airfoil problem. We can see that with the trained model, the velocity and the skin friction coefficient are almost the same with the exact solutions. In the field of weather and climate modeling, there are many physical processes at different scales. In previous study, we used multiple weather prediction model to simulate the dynamic and the physical process in meteorological climates. However, the Earth is huge and the resolution is limited. We cannot represent all the important processes within the model simulation. Up to now, we have a huge number of observation database of the Earth system. With this increasing amount of database, using machine learning method to predict weather and climate has become a hot development trend. Suppose we regard the data in weather and climate as a three-dimensional data. Then short-term forecasting can be regarded as a video forecasting in machine learning. In other applications of dynamic time series models, forecasting of time series can also be regarded as language translation in machine learning. Based on these examples, the machine learning enablers, once trained, can achieve simulation orders of magnitude faster than the original physical model. In our works, we have implemented the machine learning method to predict the sea surface temperature. We use a machine learning framework called FlowNight, which is based on the grid scale invariance in theory. FlowNight could create a data-driven reduced physical model directly from data. In other dynamics, the change in the field could be modeled as a rigid transformation. So the grayscale invariance theory could be used to predict the corresponding physical field. In our method, FlowNight is used to obtain both the horizontal velocity field and the sea surface temperature. From the above figure, we can see that the predicted sea surface temperature is reasonable and close to the ground truth. Okay, that's all of my presentation. Thanks everyone for listening.